Welcome to another mathematical meditation. I'm your host, Ted Z. And today I don't have any theorems or proofs for you, but I do have a kind of mathematical mystery that may perplex you. So Walter and Alice are doing some kind of nuclear research, and they need to do Monte Carlo calculations, so they have to generate lots of random points. Specifically, they need to generate points inside the unit circle. We want these points to be uniformly distributed, same probability anywhere, kind of like this, it's going to look uniform, doesn't bunch up anywhere, and something like that. That's pretty uniform. So this is what we expect. So let's see what Walter came up with. So here is what Walter is up to. He reasoned this way: put a box around the circle, and let's put the coordinates of these points. -1 and -1. This is 1 and -1. 1 and 1. This is -1 and 1. Okay, so the box is in gray. I don't know if you can see that clearly, but it's there. And Walter's idea is this: if he chooses a point P1 outside the unit circle, well, then it's rejected. And if the point P2 is inside the unit circle, well, P2 is accepted. How are these points generated? Well, choose X and Y randomly from -1 to 1 and uniformly. There, that should be good enough. Your point is Pxy. And so we accept P if x squared plus y squared square root is less than 1. Well, actually, I can get rid of this square root. Square both sides, I still have 1, so that's good enough. And we'll reject P if it's outside, like P1 is here. Very good. So let's see what happened with Walter's simulation. Well, that looks pretty good. This was 50,000 trials. And the result is excellent. It looks very uniform, very nice, and uniform. So I'd say this is a great success. Now let's have a look at what Alice came up with. Alice is perhaps a little bit more clever than Walter. She reasons that it's inefficient to generate points, only to reject them, because a lot of Walter's points end up on the unit circle or outside the unit circle, and they get rejected. So she comes up with a clever scheme where all the points are inside the unit circle and nothing is rejected. Her idea works like this: we choose points uniformly, randomly, along a radius. So R is some random number from 0 to 1, chosen with uniform distribution. And then we choose an angle uniformly. So this is R, for point R, and then we choose a theta, and with these two together, we end up with a P. And that P is always going to be inside the circle. Okay, so theta is chosen from 0 to 2 pi uniformly. And then my point P, well, that's just R cos theta, sine theta, R sine theta, like this. There. Alice likes this scheme because it's, in a sense, more elegant. It doesn't generate wasteful points. I'd argue that this scheme is maybe not faster than Walter's. Why not? Well, because sine and cosine are expensive to compute, like relatively expensive compared to, the squares that we were computing with Walter's scheme. But Alice likes this idea anyway, so she goes ahead with it. And now let's see what the result is. Wow. 50,000 trials, just like Walter. Why is it not uniform like Walter's result? Wow. Let's have a look at their results side by side. Well, it is indeed a mystery why these two are different. If you asked me this question before I looked into this, my intuition, which is not that great, would say, oh yeah, this is going to give the same result. Both of these things should give a nice uniform distribution. But boy, would I be wrong. Now imagine we would make this assumption in some critical research. Yeah, that would be really scary thought. Well, I'm not going to resolve this mystery in this video. I'm going to leave it to you. I'm going to leave it to you for now. Maybe I will talk more about it in the future, but why not look into it? Do some digging into articles on the internet. Why does this happen? If you find some really nice, pedagogically friendly explanation for this, then why not leave it in the comments? I would really love to read it. Okay, like, comment, and subscribe. Send me a super thanks if you like, and I will think of more mathematical mysteries to present to you, and I will see you next time.